So, Vanakkam, we will continue our lecture on engineering seismology. So, we have been discussing about the Fourier domain parameters calculation by the Fourier analysis. Okay. So, we have seen that the acceleration time is what we are getting is the consist of amplitude and duration you can interpret directly. So, if you want to understand the structural response at different frequencies or a particular structure will have a unique natural frequency, how the amplitude varies with the frequency you have to know. So, in order to know that, basically the acceleration timeicity data has been transformed to the Fourier spectrum by converting into the Fourier transformation. Okay. So, you can do with two kind of Fourier transformation. So, one is that discrete Fourier transformation and then fast Fourier transformation, where the acceleration timeicity data will be transformed by doing this Fourier transformation calculation. So, you get a Fourier amplitude spectrum and a power spectrum. So, we have been seeing that the Fourier spectrum how it is for the typical data which we have discussed even that time. So, this was the same all-over earthquake east-west Fourier component. So, you can look at basically the amplitude of this data. You can see the amplitude of the data, and also if you get here some kind of shape you can see like this. So, if you convert this into period, so you can see what we have discussed in the response spectrum. So, response spectrum we have seen that this goes like this and like this. You can see this is actually the inverse shape. So, here you are using the natural period. So, here the frequency. Okay, this is basically the inverse of the same. So, this is similarly the all-over earthquake component of the north-south Fourier amplitude spectrum. So, here also you can observe a similar trend. Okay, so, you can observe a similar trend, but here you can see that amplitudes. So, here basically the Fourier amplitude is 2.5, the highest one will be the 5. The previous one if you see the 2.2 is highest one and then the 2 is the lowest one. Okay. So, that scale you can clearly see how it is different. Okay. So, this is the vertical component, you can see the vertical component here as well as the here, and similarly the similar kind of shape you can also get here. Okay. So, this is how you get. So, when you plot this again as I told you that, so 1 by 100 is 0.01 or 0 spectral acceleration where you get like this. Okay. So, this is a response spectrum. So, this Fourier spectrum has a different application, different spectral parameters you can derive from this Fourier spectrum. The response spectrum does not describe the actual ground motion, but it does provide a valuable additional information on the potential effect of the structure for the given input. So, this spectrum is complicated function, and with the timeicity the great many are the data required to describe then completely. So, the number of spectral parameters have been proposed to extract important piece of information for each spectrum is the predominant frequency. So, a predominant frequency is basically a single parameter that provide useful although somewhat crude representation of the frequency content of the ground motion in the predominant period. Okay. So, that is the frequency content. So, the predominant period is defined as the period of vibration corresponding to the maximum value of Fourier amplitude spectrum. So, if you get a Fourier amplitude spectrum, the maximum value corresponding period is called as a Fourier. So, the predominant period. So, to avoid undue influence of the individual spikes of the Fourier spectrum, the predominant period is often obtained by smooth spectrum, while the predominant period provide some information regarding the frequency content, the motion readily different frequency content that can have the predominant period. The bandwidth, the range of frequency over which the some level of Fourier amplitude is exceed. Okay. So, we are now discussing about the predominant period. So, what is the predominant period? If you take a Fourier amplitude spectrum, if you smooth that, okay, then a particular frequency where the peak is attained, okay, are having the maximum value of the Fourier amplitude, then that period is called as a predominant period or predominant frequency of the system. Okay. So, what you should do for that actually to get it? So, you basically you can get a Fourier spectrum. Okay. So, this will be, we have seen that this is varies like this, like this, like this, like this, like this, like this. So, you can see this is basically your 100 hertz. Okay. So, this will be the 100 seconds. Okay. So, this will be the frequency hertz. So, this will be the period. Okay. So, at one point if you make the smooth of this, okay, so the where this basically is the where you are attaining the peak. Okay. So, this is basically the Fourier amplitude. So, this is the Fourier amplitude. So, this smoothing, okay, so smoothing of this data for this point is peak. So, this corresponding frequency is called as a predominant frequency or predominant period of the system. Okay. So, this is what is described in the predominant period, which is basically the peak value of the Fourier amplitude spectrum smoothed plot where you get a peak response. So, this, okay, for the frequency of the single degree freedom. So, you will get each earthquake will have its own predominant frequency of the system. Okay. So, here when we are talking about the earthquake, so there is a each structure or system also has its own natural frequency or natural period. Okay. So, that part we should be will be discussing now. So, we get a, for example, whatever acceleration time is t you are getting. So, this will have a predominant frequency. Okay. So, when you are having in the ground a structure standing like this, okay, so this will have its own natural frequency, and then you have the soil. So, this will have its own natural frequency. Okay. This is the soil. So, this is the structure. Okay. So, then the earthquake whatever it comes from the distance. So, whatever comes from the distance will travel like this and affect goes like this. So, here you can see that if this natural predominant frequency of the, so this you see that you have the predominant frequency of the input motion and then natural frequency of soil. So, some of the cases this frequency and this frequency will be coinciding. If that coincide, you will get a maximum response of the ground vibration at this particular place. So, or this combined frequency will reach a structure, it has a frequency close to the structure, okay, then this will have the maximum response and failure. So, when we are designing, we should see that the natural frequency of the soil column does not go closer to the natural frequency of the input motion expected in the region, and even the combined frequency of these two should not be matching with the your structural frequency. So, as we know, we do not know that what natural frequency the input may come, but it is easy to find out what is the natural frequency of the soil, okay, natural frequency of the structure, and we see that these two are not matching, we keep far away. So, when you keep far away, basically even if this frequency modifies because of the input motion, you will not get so much effect to the structure. So, that is what in the design they will take care when they analyze this kind of Fourier data and analysis. So, the Fourier data will help you basically to get all those things. So, the Fourier spectrum further can be used to get a other parameters which is useful for the seismology part. So, the Fourier acceleration amplitude tend to be largest over a intermediate range of frequency. So, bound for a corner frequency fc and low side and cutoff frequency f max at high side. The corner frequency can be shown theoretically. The Brun 1970-71 he designed that to be inversely proportional to the cube root of seismic moment. So, the result indicated that large earthquakes produces a greater low frequency motions than the smaller earthquakes. So, the cutoff frequency is not well understood. It is been characterized that both as a near site effect and as well as the source effect, and it usually assumed to be constant for a given geography region, which is the cutoff frequency. So, basically when you plot a Fourier amplitude log scale and the frequency in the log scale, you get typically the plot like this. So, after you smooth, you can find that your data are like this. After smoothing, you can get this point and this point. So, this point is basically your corner frequency. Okay. So, it is basically a proportional to the cube root of the seismic movement, okay, larger earthquake and low frequency component. So, this is very difficult to define, but however it is constant to the geographical region. So, this will be the earthquake based one, this will be the region based one. So, this corner cutoff frequencies are used in the simulation part and synthetic ground motion in the seismology, this one. So, you can see this is the typical earthquake, okay. So, recorded from the different part, and you can see how the your corner frequencies are changes. So, it is a function of basically your seismic moment, okay. So, the Fourier spectrum and the frequency where you get a your frequencies are keep basically reducing with increasing in the magnitude, okay. So, this is the typical acceleration history of the data which you use to get this Fourier spectrum values. So, the Fourier amplitude spectrum, the Fourier amplitude spectrum strong ground motion shows how the amplitude of the motion is distributed over a respect to the range of frequency and period is expressed as a frequency content of a motion very clearly. Fourier amplitude spectrum may be narrow or broader. So, the narrow spectrum implies that the motion has a dominant frequency or short period which can produce a smooth and almost sinusoidal time histories. So, narrow spectrum can be expected for the where you can see that. So, produce smooth and sinusoidal time history. So, imply the motion has a dominant frequency and period. Okay. The broad spectrum corresponding to the motion contain a variety of frequencies, not particular frequency, and produce a more jerked and irregular time history. Okay. So, the modeling of Fourier amplitude spectrum is of prime importance for the simulation of ground motion data. Both empirical and theoretical models of Fourier amplitude spectrums are exist. Okay. That can be used for the modeling your simulations of the ground model. So, this is the typical Fourier amplitude spectrum. Fourier amplitude spectrum and the closely related to the power spectral density combined with the phase spectrum can be described the ground motion completely. The plot of Fourier amplitude spectrum versus frequency known as a Fourier amplitude spectrum, and the plot of Fourier phase angle gives the Fourier power spectrum. So, the plot of the Fourier phase angle and Fourier amplitude with respect to the frequency will give you the Fourier amplitude spectrum and Fourier phase spectrum definitions. So, you can see here this is actually the typical ground motion, okay, recorded at rock and the soil site. You can see when you take a Fourier spectrum, you can see where it reaches a peak. Okay. So, here also you can see where it reaches a peak. So, you basically find out the, you can see your period, okay, how it varies. Even you can also verify your amplitude. You can see how these values are changes. So, it depends, it is influenced by the medium which it travels as well as to the your input Fourier content of the input, okay, peak values of the input. So, these are the way. So, Fourier spectrum empirical models. So, as you said that the Fourier spectrum has a empirical model to derive this. So, those things are like the theoretical and also empirical model. So, we will discuss those things in short form. Okay. So, detailed discussion if you want, basically if you are interested to continue your career as a seismologist, so then you need to study all those things. So, as per this class concern, we will give only a small definition and introduction what is the Fourier spectrum empirical model and a theoretical model. So, Turifinac and Lee 1989 provided empirical models of for scaling Fourier amplitude spectrum in terms of earthquake magnitude, source to site distance and site intensity and recording site condition. So, these models are based on the regression of the empirical amplitude of the Fourier spectrum. So, the empirical model basically they got lot of Fourier amplitude spectrum, and then each frequency they taken a component and try to give a model, empirical model to fitted with the data, that is a Fourier spectrum empirical model. So, that model you can use to get a Fourier spectrum in your region if the seismicity and the seismotectonics are similar if the developed data. Okay. So, the another well known model what they use is actually Fourier spectrum theoretical model. So, holistically theoretical model of Fourier amplitude spectrum of the ground motion involves the element of the source, propagation, path attenuation and high frequency domination and the site amplification. So, these are all the factors which basically a theoretical model controls. So, the basically a theoretical model of Fourier amplitude spectrum combines a source, path and the attenuation characteristic and amplification. So, this will be like you will have the rock here, this is the soil. So, this site condition when you want to get taken to soil, you need to good the site condition, otherwise up to rock these parameters basically solve the theoretical. So, here you can see that your the point source theoretical model expresses that the seismic moment. Okay. So, then the frequency content at which you are looking, the corner frequency, F is the corner. So, attenuation is expressed as the function of your frequency and then your the travel path, okay, the R. Okay. So, that is even expressed as a quality factor Q. Okay. So, again the attenuation characteristics of the path express the frequency content of the motion and then the particular frequency what you are look for and then the kappa factor, those kind of things are used. So, this parameter knowing this basically you can try to get a spectrum for a given site. So, the Y is F and R is called as attenuation factor which is the function of the YG R is actually geometric attenuation factor due to the geometric spreading of the seismic waves. At epicentral distance R less than 100 km, empirical evidence indicates that geometric attenuation is the function of 1 by R. So, the Atkinson and Silva state that geometric attenuation proportional to the 1 by R at epicentral distance less than 40 km, but to the 1 by R square root to the empirical distance greater than 5. So, this basically depends upon the region to region. So, Atkinson and Silva given for the western US. So, it is not constant throughout that. So, recently we have been derived this kind of factors for our Indian Himalayan data. You can refer our papers published in the Soil Dynamics and Earthquake Engineering Journal. We used the data and tried to derive how the attenuation characteristics occurring at a Himalayan region. That was the first unique work what we have done. So, we have been keep working on this kind of areas. So, where you get more information, but here only the concept is sufficient for the course point of view, because if you want to generate this synthetic ground motion simulations and all, you have to go in detail to these kind of things. So, the YA F and R unelastic attenuation, the whole path attenuation factor given by the following expression you can see. So, here basically, so the Q is the so called quality factor. It is a simplest definition can be taken from the constant Q equal to Q naught. So, this quality factor also one can derive from the recorded earthquake data. So, you have to estimate recorded earthquake data which will be unique for a particular seismotectonic region. So, the PF serve as a high frequency dominant vector accounts a decay of spectral amplitude at high frequencies believed to caused by the weathering of the upper layer of the medium. Bohr 1983 assigned 4th order of the Butterworth filter to find out a PF. ZF expressed a scaling factor to account site effect. Bohr and Joyner provided amplification values of the function frequency towards assessment of the ZF and typical soil parameter associated with the NHRP classifications. So, this is the way a theoretical model is defined. So, here you should understand that. So, if you have the recorded data, okay, so you can find out here your FC is the cutoff frequency and F naught is the corner frequency. Okay. Then, so from the data you can also find out a seismic moment, or if you have the corner frequency, your seismic moment is actually the cube root of the corner inverse of the cube root of the corner frequency. So, by knowing this and you can estimate your source point, okay, Fourier spectrum. So, similarly the attenuation characteristics where the quality factor again you need a recorded data. So, again the high frequency dominant domination factor K kappa factor, that is also is the function of data. These parameters generally if you have the large number of recorded earthquake in the region, so you can get all those data and try to process and get this kind of factor estimated. So, as per your so the class concern, you should know what is the this happens in the this entire Fourier theoretical spectrum. Okay, that is sufficient. You don't need to mug up any of this equation. The definition of corner frequency, cutoff frequency, what is mean by quality factor, QEs are important. So as per India concern, very less researcher working on estimating this kind of factors using Indian data. So first of all, the data available in Indian regions are very limited. Okay, so even among the limited data, so this kind of analysis are very less carried out. So most of the people who you use synthetic ground motion simulation or use this kind of factors in their analysis, they simply take factors derived from the elsewhere and use it here as a input parameter for that. So the first time actually we have did a very regressive analysis of the data collected from the Himalayan region and then try to estimate all these factors for the Himalayan data, and which we also published and used to generate a synthetic ground motion, and then that ground motion we used to get a predictive equation for the ground motions, okay, at a different frequency or period level. Okay. So the simulation of the synthetic ground motion and the models which used for the simulation of synthetic ground motion will be discussed in the next class. So today class what we have seen, basically we have seen that the spectrum, okay, whatever data you are obtaining, okay, so from the acceleration time history you can transfer that to the Fourier so spectrum. So by in form of Fourier amplitude versus the natural frequency, okay, or frequency content of the your ground motion. You can see that these Fourier amplitudes are peak at a particular frequency. Okay, so that is called as a your predominant frequency or predominant frequency. Okay, predominant period or predominant frequency of the your input motion. That data you can get from this analysis. So then when you plot a Fourier spectrum, you can also notice that it follows a inclined portion, then horizontal portion and vertical portions. So that data is basically will give you the idea of corner and cutoff frequency. The corner is termed as FC and cutoff is frequency is called as a FC, and corner is named as a FO. So this corner frequency is the function of seismic moment at your source. So that means if you know the corner frequency of the particular place, you can try to get what is the seismic moment. So from there you get a Fourier amplitude per a given frequency. So if by generating lot of Fourier amplitude, you can also see that how this amplitude varies with the time. And then the quality factor and then the kappa factor, which is the function of basically your regional seismic data which need to be estimated. Okay. And we also see that the attenuation character, okay, 1 by root r or root r, so which is basically is the function of your regional level data. Okay. So we have observed that it has been reported in US for up to like less than 100 km 1 by root r, and but that it has been proved that it is not constant. So up to 40 meter only with 1 by root r, the other place it's different. So that is the derivation. So this kind of parameters are individually region wise, it keep varying. Okay. So you have to estimate those parameter and try to get a Fourier theoretical model which will be useful for simulation of the ground motion at a site. Okay. So basically these parameters, Fourier amplitude spectrum, Fourier analysis and Fourier parameters of corner frequency, cutoff frequency and then predominant frequency, all those data are useful basically to get a simulations of the ground motions, which we will be discussing in the next class. So with this we close this class. Okay. So we will be discussing the source model, simple source model and other things in the next class. Okay. So far whatever we have seen that, so we try to understand the earthquake. Okay. What is the earthquake hazard, what are the hazard it is caused. Okay. So how this you can measure the earthquake, how you can interpret, how to identify the earthquake. So with this actually the complete seismology part with respect to data is over. So hereafter what we are going to discuss is how this data will be used for the getting a application side. Okay, how these parameters, whatever frequency domain parameter and time domain parameter will be used to get a earthquake simulations or earthquake hazard estimations or structural analysis point of view. Okay, so we will be basically studying how these data will be converted, whatever magnitude, intensity, so the duration, peak amplitude. Okay, so then the Fourier amplitude. So all these data will be how useful for getting the simple model parameters and simulations, and useful to arrive a design parameters for the practical design application. That will be discussed in the coming classes. So with this we will close your today class. Thank you very much for watching this video. So we will see you in the next class. Okay, so this mathematical form explained in this class basically is slightly more advanced stage, but you should know that, okay, that is what, because since this course also offered to the BTech students of civil or any other branch of the civil who are interested. So those people will be willing to proceed their career on the engineering seismology part and simulation part. As I also tell you, the research gap, okay, though somebody want to work on seismological part of Indian data and all. So for them this is the introductory part, it will make them to study further in the master level and PhD level. So most of my students basically they do research on this area. So we have been working to develop synthetic ground motion since my PhD. So we have done a synthetic ground motion generation for the Bangalore region, which is peninsular India. We have done for the Lucknow region. We have done for the entire Himalayan region as well as the peninsular Indian region, where large amount of the synthetic ground motion data has been used in the absence of the real earthquake record. That has been further used to derive ground motion prediction equation, and then understand how the spectral acceleration changes with the different period of the structure. Those are all the research are linked with that. So this mathematical form you no need to worry, only you need to know the definitions. Okay, so how it varies and all those, particularly the wordings which is given in the different color underlined portions will be important with the exam point of view, which you have to pay attention. Okay, so remaining formulas and all you no need to mug up anything. There is no formula will be asked in the exam point of view. Okay, only the simple and straightforward formulas which you can remember will be asked in the exam point of view. So with this we close the mostly the seismology part of the course, understanding earthquake, measuring the earthquake and interpreting the earthquake recorded data, how to quantify earthquake, scaling the earthquake, all those things part we have completed as on today class. So the next class onwards we will be using all this study, whatever information we have studied will do for the application of the different part. Okay, one is that prediction of the earthquake hazard, another one is the simulation of ground motion. These two major application will be looking at in your course. So for that application, whatever the background knowledge we have learned will be helpful to you. I request you to closely monitor the classes. Whenever you have doubt on particular things, you can go back to the video and check. In case even if it is not clear sometime, you can talk to TA or approach me, so that we will be interacting and try to understand better. Okay, so many of you, your mathematical background may not be that level advanced as the master level and PhD level. It doesn't matter. Okay, only you should know how these things are working. I always believe that all whatever theoretical models, okay, like wave propagation theory and this attenuation theoretical models and all with a lot of assumption, okay, which practically doesn't match with the practical condition, only to help you to understand how it works. That understanding you are making, it's okay, no need to make a derivation and all. Derivations you can find out in the standard textbooks, or even you can find out in the website. These days everything is available with the MATLAB coding, but you should know fundamentally how it works. That is what very important, not the mucking up the equation. Okay. So with this remark of all our so far classes, so we will close today class. So I will request you to go through all the material part, so that next application side will be very clear. So thank you very much for watching this video. I look forward meeting you in the next class. Thank you very much.